Okay, if you just hopped on, we're going to get started in a second. So just bear with me. Just trying to get this pulled up. Okay, we should be good to go. So I'm going to give people a minute or two to get logged on. And if you have questions at any time, remember that you can always send me messages on our Mind or use the live chat on YouTube. You just need to be logged into your YouTube account. So we'll give everybody about another minute and then we'll get started. Today we're going to talk all about the fundamental theorem and the various parts of it. So hang out, grab a snack if you want one while we go through this, and we'll go from there. Again, if you just hopped on, we'll get started in a second. We are talking all about the fundamental theorem today, but just bear with me. I want to give everybody about another 30 seconds to get on, and then we'll start. Okay, so let's get going. Let's see, if you have questions at any time, send them. But we're going to get started and talk about the fundamental theorem. So the fundamental theorem must be important. It has fundamental in its name. And this is really going to bring together everything that we did in the course from derivatives and integrals and put them together into one. So let's briefly look at what the actual theorem says. Here's the fundamental theorem in all its glory. So different books use different parts, part 1 versus part 2. Sometimes they swap the order. I'm not really worried about what part it's called. I'm worried that we understand the theory of it. So suppose that a function f is continuous on interval I containing the point A, and capital F is the antiderivative of lowercase f. So in other words, what that means is that the derivative of capital F is lowercase f, right? Because f is an antiderivative of 1. So if we take the derivative of an antiderivative, what the fundamental theorem says is we get back the original function. And we're going to talk a little bit more about that, but what this is basically saying is that derivatives and integration are inverses of each other, right? And so we can undo taking a derivative by integrating, we can undo integrating by taking a derivative. Now, part 2 is where we get more into applications, which is if g of x is any derivative of f, then g prime equals f, right? Or any antiderivative, I'm sorry. Then for any b value on the interval, the antiderivative of f from a to b, or the integral from a to b, will be g of b minus g of a. So what that says is take the antiderivative, plug in your upper bound and your lower bound, and that will give you the net change or the area under the curve there. So if I look at something like this, we've evaluated lots of these. So if I go from 2 to 4 and my, function is 2x with respect to x, then the antiderivative of that would be x squared, and I would evaluate it from my lower bound to my upper bound. So this is where this idea of evaluating integrals this way comes from, right? That we could actually take that, plug it in, and get a solution out. So those are the two things we're going to try to be bringing together today. And a lot of that's just going to be making sure we know mechanics and then applying it. So I want to look at this problem first. This is something that sort of starts to tie together the geometric with the algebraic, and then we're going to do some algebra from there. So graph of g of t from -2 to 3 is shown, and we're going to shade the region bounded by these. So first of all, the region I'm talking about is this on the positive side, right? And then this on the negative side. And so typically, depending on where I was taking my integral from, I would consider this green part positive if I go from left to right because it's above the x-axis. And I would consider this red part negative because that's below the x-axis. And again, this only counts if I'm going from left to right. So remember, direction matters. Now, I'm going to fill in this chart that we see here by actually calculating the areas. And notice where I'm taking the integral from. So capital G is the integral from 0 to x of 2t. So the variable here in this function is x. The variable is your upper bound, right? 2t is not a variable. It is always going to be the function 2t that we're finding the area underneath. So looking at these, usually it's easiest to start from 0 because that's where this actually starts out. If it was the integral from 2 to x, you might want to start at 2. But here, looking at this, the integral from 0 to 0 will be 0. And then going this way, those areas should be positive because we're accumulating positive areas over on this side. Now, if I go this way, I know that those areas are below the x-axis, but since I'm going from right to left, those are actually also going to be positive. And so those are the areas that I wind up having using just the area of a triangle. So if in general I wanted to find this, what I would really be doing is the area of a triangle, which would be 1/2 of the x value times the y value, which would be 2 times whatever x is. And then I would be taking the absolute value of that, right? That's really what I'm doing here. So this winds up being 1/2 of 2, and that's x squared, okay? We don't actually need the absolute value because if we have a negative x value and a negative y value, those will cancel each other out because we're squaring it. So that is my general formula for this g. And so what's interesting there is I started with lowercase g, which was 2t, and I found the integral, the area, the net change, and look at my general formula for that. It was x squared. And so we know that from looking at, general antiderivatives this year, but that g would just be the function x squared. And if we actually graph this, if we graph those areas, it would look like x squared, right? That's what your original function looks like. Now, what does that mean g prime is? Well, g prime, if that's x squared, would be 2x. So look at where we're starting. We're starting with lowercase g, which is 2t. We're finding the antiderivative of that from 0 to x, which is x squared, and then finding the derivative of that, which is 2x. So notice the only thing that's really happening here is we rewrote this in terms of whatever our bound was, right? So this is sort of where the fundamental theorem gets generated from. Now, what if the bounds aren't just x? Well, then we need to think about the fact that we've got some chain rule going on because there's basically a u sub happening here where we're plugging u in for our output. So h prime would be f of u times du because this is chain rule, right? Derivative of the outside, leave the inside alone, times derivative of the inside. And so in our case, that would be this. So what you really need to think about when you're taking the derivative of an integral is that I'm starting with this, which is an integral defined function. And remember here that that means that it's really h of the upper bound minus h of the lower bound, right? So we're plugging that in. If I take the derivative of that, it would be the derivative of this integral. And so what that would really be would be h prime of b of x times the derivative of the inside, which is b prime of x, minus h prime of a of x times the derivative of the inside, which is a prime of x. So that's where we're going to kind of start out here. Let's do some practice with taking the derivative of an integral and making sure that we remember that we need to take the derivative of those bounds when we do it. So let's look at a couple of these. We want to find f prime. So if this is my function f, then I want to take the derivative of that. Well, the derivative of an integral, those should undo each other. And so this is going to be f prime. It's going to stay the function in there, so that's 3, times the derivative of the upper bound, which is 1, minus 3 times the derivative of the lower bound, which is 0. And so this is just 3. So the derivative of that integral is just 3, or of that integral defined function. Now let's look at this one. Let's see if this changes anything. So same function. So the derivative of that, the function will stay the same. And the derivative of the upper bound is 1 minus 3 times the derivative of the lower bound, which is 0. And so this is still 3. And so notice it doesn't really matter what that lower bound is, as long as what's happening is, my upper bound still just x. All right, let's look at this one. So f of x is the integral from 0 to x of 2t. So f prime of x, well, the derivative of an integral will be the same function, but I'm going to plug in my upper bound times the derivative of the upper bound minus the same function, plug in the lower bound times the derivative of the lower bound. And so this is just 2x. Okay, same thing on this one. So f prime here would be the function staying the same because you're taking the derivative of an integral. So plug in your upper bound, multiply by the derivative of that, minus plug in your lower bound times the derivative of that. And so these have the same derivatives because we are looking at the fact that their lower bounds are both just constants. Now, let's take a look at one of these. So let's say I look at this one here. So now f prime, well, remember that derivatives and integrals undo each other, so that function will stay the same. But we're going to plug in our upper bound. So 2 minus 2x times the derivative of the upper bound, which is 1, minus, plug in your lower bound, 2 minus 2 times 0, times the derivative of the lower bound, which is 0. So this is just 2 minus 2x. Same thing on this one. So I'm going to start by plugging in my upper bound. So 2 minus 2x times the derivative of the upper bound, which is 1, minus 2 minus 2 times the derivative of the lower bound, which is 0. So the thing I want you to notice about these is it really doesn't matter what your lower bound is, right? That's not really significant. If your upper bound is just x and your lower bound is just a constant, what we wind up with is that the derivative of that integral is the function with the upper bound just plugged in. Now, let's say that we look at some more interesting ones like these down on the bottom, where we have a upper bound other than just x. So if I have this, it's going to be the same thing. So f prime will be, now remember your function will stay the same, but we're plugging in the upper bound because when you actually take the integral, you would need to do that. And then we're multiplying by the derivative of that upper bound, and that comes from chain rule, minus 2 times the lower bound times the derivative of the lower bound, which is just 0. So this would be 18x. Now let's look at this one. So this same function, different bounds, so f prime would be 2 times the upper bound times the derivative of the upper bound, which is cos. And we can start to see that, okay, this would be 2 times the lower bound times the derivative of the lower bound, which would be 0. So this is just 2 sine cos. So starting to put this together, if you've got a constant in that bound down there, then f prime here is just going to be f of the upper bound times the derivative of the upper bound, which is just 1, right? If you have a function in that upper bound, but still a constant in the bottom, this would be f of g of x times the derivative of g of x. Again, minus 0 because that a is there. Now, let's do one where we actually have functions in both bounds, and then we'll move on to actually doing some interpreting. So here, looking at these bounds, let's say I go from sine x to tan x, and my function is radical t dt. Okay, so this is my f of x, capital F, and I want to find capital F prime. So your function is radical t, and that's going to stay that way, but we need to plug in the upper bound, multiply by its derivative. So this will be square root of tan times the derivative of that, which is secant squared, minus, now we're going to plug in our lower bound, times the derivative of that, which is cos. So this would be your full derivative there. So something to remember is this idea, right? that when we take an antiderivative, or we have the subtraction, and when we take the derivative, we wind up using the chain rule. So when you are actually calculating these derivatives, you will have the subtraction and the chain rule in there. And sometimes some of them cancel out because the derivative is just 0, but in general, that's where we're starting out. So feel free to send questions along. Again, this is like deep diving back into fundamental theorems. Some of this may look familiar, but we're really going back to like what were the basics with fundamental theorem. Now, here's the next thing we want to remember is that we know that derivatives and integrals have this inverse relationship, right? So we're going to start looking at what do these things represent. So h is the rate of change of the height of a conical pile of sand measured in feet per hour. Units are a pretty dead giveaway here, and h is already a rate. So this kind of in your mind, think this is already a derivative, right? It's already a rate. Now, what does the integral from 0 to 5 of h of t represent? And we want to answer in correct units. So let's think about this. H is the rate the height is changing in feet per minute. So the integral of that should be the net change, right? So this is the rate. So my actual integral will be the amount of change in height. So this represents the net change in height of the pile of sand. And let's think about our units. The rate of change is in feet per hour, right? So my rate should be in feet, my amount should be in feet. And we need to think about what the bounds mean, right? So that's kind of what the antiderivative of h is. But what the heck are these bounds? So we're going from 0 to 5. And notice my units of time are hours. So from t equals 0 hours to t equals 5 hours. And that's really how I would describe that. It's the change in height of the pile of sand in feet from 0 hours to 5 hours. We don't know if it's going up or down. We just know that's the net change. Okay? Same thing if we're talking about something like velocity, right? Velocity of a particle moving along the x-axis measured in feet per second is v. What does the antiderivative or the integral of that mean from 3 to 10? So think about it. Velocity is sort of the derivative. It's already the rate. We're finding the antiderivative, so that has to do with position. So I would be looking at the net change in position. I would be looking at the displacement, right? So that is the net change in position, or you could call it the displacement. It is not the distance traveled. That's something different, right? The displacement of the particle from in feet from t equals 3 seconds to t equals 10 seconds. And all of that stuff is important. You need the time, you need what it represents, you need the units. So make sure that you have all of those sort of in there. Okay, so let's look at ones like 4 and 5 where we actually have a situation. So v of t is the velocity, and the position is 5 at time t equals 2. Anytime you see something like that, think, that looks like an initial condition, right? So this says write an integral expression that represents the position of the particle at 10, and write an integral expression that gives the total distance traveled from 2 to 10. So let's start with finding the position at 10. So I know that the net change will be the change from 2 to 10 of of v of t. So that's the net change in position. But my starting position was 5, so I need to add that in. Integral expression means you don't need an equal sign, so that would totally suffice for an integral expression. Now for b, then we would say, okay, write an expression that gives the total distance traveled. So the integral from 2 to 10 of v of t dt, that is the net change, right? That's not the total, that's the net. And so to make it so that we don't care about whether we were moving in a positive or negative direction, we can throw absolute value bars around that. Because think about it. If you had a position function that looked like this, what the absolute value would do is it would say, okay, this is positive, leave it alone, but this is negative, let's flip it up. And then all your area under the curve would be positive. So that, when you're talking about total change in position or total distance traveled, throw the absolute value bars in there. Okay, last one. P of t is the rate of growth of the rabbit population measured in rabbits per year, and there are 100 rabbits in 2005. Write an integral expression representing the rabbit population. So it's important here that it notes that 2005 is year 0. So I would be looking for the net change between 0 and 2 years later, 2007, of P of t dt. And I do have an initial population. It was 100, so that would be your initial. So this really involves you understanding that relationship between derivatives and integrals and that they're inverses of each other. And if you know all that stuff, then these become much easier problems. Okay, take a second, see if there's anything you have questions about, and then we're going to pick a couple of these. We're not going to do all of them, but try to make some sense of these using the two things we know about derivatives and integrals from the fundamental theorem. Okay, I'm not seeing any questions, but again, feel free to send them through. I know you guys are out there, so send them through. If you're watching this on like a rewatch, feel free to send them to me later, even if you are watching it then. So what I want to do is look at two different ways to solve these. So I want to really look at those as ways to use the fundamental theorem to your advantage. And that idea of knowing what the fundamental theorem says and the relationship between derivatives and integrals will help us. So let's look at problem 1, and we're going to set these up. We'll integrate maybe one of them, but let's see how these work. So looking at the first one, it says solve by both methods. So at least the first one we're going to do in both ways. So here what I've given you is I've given you the integral, right? And I've given you an initial value. So a lot of you guys will think when you see something like this to go right to this. Y of 1, because that's your starting value, plus the integral from 1 to some other place of y prime dx. And I'm just going to actually write what y prime is. So 2 plus 1 over x squared dx. So this is your initial, and that's your net change. And we've definitely talked about that in my class a ton. Now, where are we going to? So I want to know the value at 3. I know the value at 1, right? So what I'm looking for is the net change from 1 to 3. So if I wanted to just do this by going straight to what I know, initial plus net change, we could do this. Now, the other way to do this is to say, okay, maybe I forgot this initial plus net change thing. But we have this puzzle from the fundamental theorem, which is that the integral from a to b of this, because that's y prime, right, should be y of our upper bound minus y of our lower bound. So if I set up an integral here, if I set up the integral from 1 to 3, then that should be y of 3 minus y of 1. And then you could say, ooh, I already know this y of 1 value. This is 6. And notice what happens. You wind up adding 6 to the other side, and you get exactly what you started with up here, 6 plus the integral from 1 to 3 of that. Now, for the sake of time, and because I assume we can take an integral, I'm not going to do this one. But when I say two ways, those are sort of your options for how you could set that up. They are equal in my eyes. It doesn't matter to me which one you use. As long as you can kind of work your way through that puzzle, which is how do you find a missing value given the derivative and an initial value. Okay. So let's set up another one. So let's say we were doing f prime here is cos 2x, and f of 0 is 3, find f of pi over 4. So again, you've got two options. You could say, okay, my initial's at 0, so f of 0, plus the net change from 0 to pi over 4 of cos 2x dx. And I hope that that's calling out to you that you would need to use a u sub there because of that 2x. Or you could say, okay, the integral from, what are my two values, 0 and pi over 4 of cos 2x is going to have to be f of the upper bound minus f of the lower bound. And we know f of the lower bound is 3, so we could plug that 3 in there, and you wind up with the same expression, right? So either way, that would work. Now, this is exactly the same as if I give you something like number 3, where I say this is your rate of change. There are 150 gallons initially. We know that means that's our initial. How many of gallons are in the tank at 24? So this would be 150 plus the integral. We're starting at t equals 0 and going to 24 of dw dt dt. And from there, you could actually do your antiderivative and go. So same thing on a bunch of these. And they really don't get much different. Let's see if there's any that are more interesting here. Position, we know the initial, find the position here. They're all exactly the same. Some of these just let you use your calculator. So the last thing I want to do is look at some graphical ones, and then we're going to call it a day for now on this. So the graph of f prime is the semicircle shown at right. Find f of negative 4 given that f of 4 equals 7. So think about what we know here, right? We know our initial, which is f of 4. And I want to find the net change from 4 to somewhere of f prime. Now, to where? Well, we want the value at negative 4, right? So that's going to be my upper bound. I know that integral looks backwards, but that's okay. Because think of what's happening. We know the value of f at 4, and we want to go backwards to see what the value was at negative 4. So it makes sense that we would actually be working backwards here, right? So this is 7, and that integral, well, first of all, we're going right to left, and it's above the x-axis, so this will be negative, and then it's 1/2 pi r squared. That's your area there. So this would be 7 minus 8 pi, and that would be f of negative 4. All right, let's do one more graphical, and then unless you guys have questions, I'm going to be out of here. So the graph of f prime consists of 2 line segments and a semicircle. Given that f of 2 equals 5, find these values. Sorry, f of negative 2. So this is your initial. So to find f of 1, I would be doing f of negative 2 plus the integral from negative 2 to 1 of f prime. To find f of 4, I would be doing f of negative 2 plus the integral from negative 2 to 4 of f prime. Or you could take your last answer and just add in from 1 to 4 on there. And here, I'm going to do f of negative 2 plus the net change from negative 2 to 8 of f prime. Or you could take your last answer and just add the change from 4 to 8. So again, more than one way to do a bunch of these. So let's find some areas. So this triangle right here, that is 4 by 1, 2, 3. So 6, right? 1/2 4 times 3. This one is 1, 2, 3 by 2. So this is 3 because it is 6 divided by 2. And here your radius is 2. So this is 1/2 of pi r squared. So in other words, this equals 2 pi. So let's figure out these amounts. So for A, we would have 5 plus the net change from negative 2 to 1, which is positive 6, so that's 11. For B, we would have 5 plus the net change from negative 2 to 4, so that's 6, and then that's going to be minus 3. And so that is going to be 8. Notice you could also say, ooh, that is 11 minus 3 because this is the 11 from right there, right? So you could do that too. And then C would be 5 plus 6 minus 3 plus 2 pi. And notice that's 8 plus 2 pi. The 8 just comes from that up there. So you don't need to sort of reinvent the wheel on each of those steps. But just showing you in case maybe you weren't built up to that level. Okay, So that was a quick little half-hour crash course on the fundamental theorem. Hopefully that walked you through some stuff shaky on or you needed to know. I'm going to hang out for about 30 seconds unless you guys have any more questions. I am going to hit the road. And I hope everybody's having a good break. Last call, guys. All right, huge shout out to all the people who watched live. I hope you're having a great break. I hope that you are watching Game of Thrones and going to see Avengers and all that good stuff. And I will see you guys Monday. So please send me questions. And next live stream is tomorrow. Have a good one.